I want to start with a simple analogy. When we eat food, this food might consist of dozens of ingredients, if not hundreds. But when we try it, our brain classifies the food immediately as sweet, bitter, hot, or salty. It is much easier for us to classify and describe the food in terms of its taste. Those are principal components of the food that we could use instead of listing all of the ingredients. We would say the food is mostly sweet and a little bit hot. This information will inform much better your friend if they want to try it, compared to giving them the long list of ingredients. The same way, the principal components extracted from the data provide the information in order of importance. Now, how do we know that something is important in the data? The importance could be determined by the minimal variance of the data along some direction. In other words, the data will be very consistent along this principal direction. Other directions with high variability of data, or you could say noisy, are less trustworthy. So let's see how it looks like. When we have some data described as points in n-dimensional space, we want to fit them into n-dimensional ellipsoid. In 2 dimensions, let's say you have something like that. So you have xy axis, and then you have all kind of points, data points in that space. You want to fit 2-dimensional ellipsoid to that thing. 2 principal directions that you will get are those 2 axes of that ellipsoid, major axis and minor axis of the ellipsoid. In other words, we took all of the data, which are the points that we have here inside of that ellipsoid, and we identified first of all the direction which has minimal variance. And this means that all of the points are not that far from a specific line we are talking about, and this is the direction. So all of those points on those lines are close enough to the major axis of the ellipsoid. Now, second direction, which is orthogonal to the previous direction, this is that direction, and this is the second direction of distances of points from that middle line here. So those are principal directions which describe data in the most compact way. The derivation of algorithm needs deeper understanding of orthogonalization and projection process, so I'll provide you with practically useful answer without proving it here. Let's assume that the data is described by row vectors v, like that. Every vector will include basically n components. Now, we have m data points and we can stack them together to create a matrix V. So this is the first point, second point, until you get to the last point, which is mth point in the data. And each one of those points is clearly n-dimensional. The next step would be computing the covariance matrix C, which is defined by covariance of matrix V. Now, how do you actually compute that covariance of matrix V? Covariance V could be computed as multiplication of V tilde transpose by V tilde. Now, V tilde is computed from the matrix V. So now let's explain what it includes. Is the matrix V after subtracting from each column its average. It means that I'm taking the first column like that, computing average of that column, and then subtracting from each x. So it's x1 minus average of the column, x2 minus average of the column, and so on. Then I'm taking second column, computing average of the second column, subtracting the average from each element of the column, that mean value, and so on, getting to the third one, fourth one, and so on. And from each column I'm subtracting its own average. This will create a new matrix normalized matrix, normalized by the mean values, I will call it V tilde. So if I'm doing V transpose V of that kind of matrix, I will get covariance matrix. Clearly there are other special methods to compute all kinds of covariance matrices, but we will not get into that topic. Now, next step would be finding eigenvalues and eigenvectors of that covariance matrix C. So you will have n eigenvectors and n eigenvalues. You need to take all of those eigenvalues and sort them in descending order from the largest one to the smallest one. Since each eigenvector is associated with specific eigenvalue, you also will have those vectors sorted in order of correspondence to the largest value, a little bit smaller value, even smaller value, and so on. So those corresponding eigenvectors will show you the principal direction. If you will normalize it to size 1 or to norm 1, they will show you the direction of principal components. So that's all about PCA algorithm, and now we will see some simple example of it. Let's say you have coordinates of points in two-dimensional space, and you have totally 15 different points. Their coordinates are given by x and y vectors, so each vector is basically 15 by 1, and this one is also 15 by 1. And numbers are given here, and you can see basically x plotted as a function of y, and those points are given in space here on the plane. Now, matrix V will have only two columns. One will be x column, and y will be y column. So it will be basically matrix, which is 15 by 2. I just stuck together vector x and vector y. I want to do principal component analysis on those two vectors and matrix V. So first I'm normalizing every column, and I have two of them, by the mean. So I'm taking the original vector x and subtracting mean of that vector x. Taking vector y coordinate and subtracting mean of the y coordinate of each one of those. So every element here will be subtracting the mean, and every element here will be subtracting the mean of the second column. Pay attention that in that case, you will get all of the points shifted around the origin. So this is the origin, 0, 0 point, and all of the points now are distributed around that origin, where in previous one it was distributed somewhere else. Now I compute the covariance matrix and the appropriate eigenvalues. So I have two of those, since this is matrix 2 by 2. I have two eigenvalues. One of them is 12, another of them is 548, and the appropriate eigenvectors. So the first vector which is appropriate to 12 is this one, and this one is the second one, which is appropriate to 548. Now pay attention that this one, this eigenvalue, is much smaller than the second one. So lambda 1, and this one is lambda 2. So lambda 1 is smaller than lambda 2, which means that lambda 2 is much more important direction. Now, let's see what are those directions. The direction of lambda 1 is this one. It's minus 0.72, minus 0.69, which means it's pointing both to negative direction and negative direction in x and negative direction in y. So this is the arrow that we have here. This is the unit vector into that direction. Second eigenvector is pointing into negative x and positive y, which means it's pointing that way. Pay attention that they are orthogonal, which means you have 90 degrees always between those two vectors of eigenvectors. So this is less important principal direction, and this is more important principal direction, because eigenvalue here is larger, and this is appropriate to longer axis of the ellipsoid that we have here, and shorter ellipsoid. So it probably should be something closer to that. This is how PCA works. Now, additional things that you would like to do with PCA is to align the data with the axis that you have, which means you want to align principal axis with x-axis and y-axis that you have in the plane, or you can expand the same idea for multidimensional space. So how you do that? You need to transform your original matrix V by multiplying it by those vectors stuck together. Now, what are those vectors V1 and V2? Those are basically eigenvectors of the problem. So if you multiply matrix V, which is your original matrix with all of the data points, by the matrix which is created from your eigenvectors, you will get those red points here. So you will basically rotate that ellipsoid that way from your original ellipsoid, which was that way, and also shift it. So it's automatically shifting it to the origin, which is here, that point, shifting and rotating that ellipsoid and aligning it with aligning the data with the axis. So this is very important to find, for example, different things. As example, it could help you to classify different points into one class or another in a much more easier way than where they are not aligned with the axis.